Hey everybody. Um, Thanks for coming. So today is going to be the first of 3 days of workshops about how to use YT, starting with getting installed, getting a couple packages up and running, and then moving on to visualization and analysis. So um, today we're going to cover a couple different things, and I should note. Well, I'll tell you that in just a moment, but today we're going to start with setting up an environment. So those of you that are already comfortable using Conda and so on may have experience with this and may be able to check out a little bit. But we're going to start with getting set up with a Conda environment specifically for YT, although of course this works inside others. We're going to talk about how to install a couple helpful packages that can help us a little bit with what we're doing. And then we're going to talk about how we can load up data and what the different data means. At the end of each day, I will take the notebooks and so on that I've created, and I will check those into a repository that would be accessible online. And additionally, I will I will get these all um, online, the talks. So I'm going to have them exported over to YouTube, and I'll try to cut out the intro bit so that you can just dive right in, and I'll work on adding chapter support as well. So a couple things. There are two different chat channels that are accessible. The first one is through the Slack, and I know some of you are already on there. If you want to ask questions on Slack, go ahead and do so. I will also have the Twitch chat open, so please feel free to ask information here in Twitch as well. So, okay, let me see, where did the chat go? I just said that I would have the chat open, and now I can't seem to find it. So, I guess I'll have that over here. Okay. All right. So if you have any issues with the stream or anything like that, please go ahead and let me know. I'm going to go ahead and switch over to a clean environment. Oh, and I've got music playing in the background. Let me see if I'll go ahead and turn that off for now. Oh, you'll still be able to see it there in my status screen. But okay, so I'm going to take the approach that we're going to start out with um, a with Conda already installed, but not necessarily a clean Conda environment. So what we're going to do is we're going to start out by setting up a new fresh Conda environment. And we do that by typing conda create. Now let me make my text a little bit bigger. And we're going to create a new Conda environment, and we're going to set it up to be version Python 3.11. So for the purposes of our Intro to YT workshop, I'm going to create a new environment, and I'm going to specify the -n option, which lets me say the name of that environment. And I'm going to call this YT Workshop 2023. You don't have to call it that. I tend to call my Conda environments much simpler stuff like Pi311 and things like that. But I'm going to create -n YT Workshop, and I'm going to specify that my version of Python is 3.11. So a couple things that I want to point out here. I'm saying Python equals, not Python equals equals. And I'm also creating it with a name. So this is then going to go ahead and create a full Python environment for me. And it might download some packages. Some of them may be cached, but we'll see. I will now proceed. You'll see that it doesn't actually install that many items. So this is the base level set of information, set of packages. And now I'm going to activate that environment. And so now any commands that I execute after this are going to be executed inside this environment. I want to mention that I am going to be unsetting my Python path, but that's not something that you'll probably have to do. We're going to install a couple packages just to get us going. We're going to install YT, H5Py, and then just in case, we'll install Cython and JupyterLab. I'm going to go ahead and put this in the chat. This will download all of the appropriate dependencies and packages. And I'm just going to go ahead and let it install. And so it's installing it into its own Conda environment. So at the end of the day, I can go ahead and remove it if I decide that I want to. And it does that pretty quickly. Right now, it's going ahead and uncompressing a ton of stuff. And I'm going to do a couple more things. We're going to install an application called Widgets, but you'll note that I'm using pip here. Widgets, which is spelled in this particular case Widgyts in a delicious pun, is a YT specific set of widgets. Doesn't do a ton of stuff, but it does do some things that are quite useful. And we'll see that in just a few minutes. And we're going to do one final thing before we move on. We're going to install a Jupyter kernel. We're going to say python-m, and what that means is Python executing the module ipykernel. And what that does is it installs a new kernel that is available inside our JupyterLab interface. And we can give it a name, and it's tied to a particular Conda environment. Now, I'm sure that there are people that out there who are watching that know of better ways to do this, that perhaps integrate more nicely with Conda environments, but this is the way that I'm going to do it. So please feel free to go ahead and do it or suggest something different if you'd like in the chat. This is the way that I've taught myself to do it, so I'm going to stick to that. I'm going to say python-m ipykernel --user, which means install it just into my user configuration directory. And then I'm going to give it a name, and I'm going to put the name in quotes. I'm going to call it YT kernel. Oops, I forgot one thing. I actually need to say ipykernel install. And this is the last command we're going to do in our quest to install YT in a clean Conda environment. At this point, I'm going to create a new directory that I'm going to do all my stuff in. I'm going to cd into that directory, and I'm going to type Jupyter Lab. From here on out, we're going to be doing most of our work inside the Jupyter Lab interface. I'm going to create a new notebook. You'll see that I'm in an empty directory because I just CD'd into an empty directory. And we're going to get started with a brand new kernel. I'm going to call it Day 1, Notebook 1. Let me pause just for a moment. If anybody has any questions, go ahead and ask them. Yes, this session is being recorded, and I'm going to export it to YouTube. So if you need to hop off, or if you'd rather watch it in 2x, 3x, 10x, whatever, of course, it will be available for that. So we're going to get started with import YT. Now there are some things that might be a little bit different about my notebook than yours, but for the most part I'm going to be using pretty vanilla Jupyter Lab. I am using the Jupyter Lab interface for a couple reasons that you'll see in just a few minutes. YT has a catalog of data that is accessible, and we are going to avail ourselves of that. So the very first thing we're going to do is we are going to load a sample data set. And it wouldn't be a YT tutorial if I didn't load my absolute favorite data set of all time, Isolated Galaxy. Oops. We need to install one more package. It requires the Pooch package. So I'm going to go back to my command line, type conda activate YT Workshop 2023, and I'm going to say conda install Pooch. I thought it was a transitive dependency, but it turns out it is not. Oh, Clément just let me know that we also need pandas. So once Pooch is installed, we will also install pandas. Earlier today when I was testing this, I started with an environment that installed Napari, and Napari grabbed both Pooch and pandas. So let me go ahead and get pandas as well. Okay. So let's pretend like that never happened. We're going to install YT, and we will load Isolated Galaxy. I've also put in the chat the additional command that I needed to run. And so now we have a data set. This data set is an ENSO data set. I will say that even though we start out with ENSO data sets, I know not everyone uses ENSO. We are going to very rapidly move on to a different type of data set. This one just happens to be my favorite. So let's take a look at what our data set is. Our data set references something on disk. In just a moment, I'll show you what that data set looks like on disk so that we can compare and contrast what is available. But you'll note that as soon as I load it in, by default, a number of pieces of metadata are output. For instance, the current time is output, and that's in code units. So when these simulations are evolved, oftentimes there's some other non-seconds based time unit that is used. The domain dimensions for an ENSO dataset refers to the dimensions of the 0th level, so the base level. ENSO is an adaptive mesh refinement simulation. When we load up a particle simulation, you'll see that it has a different set of domain dimensions because particles aren't indexed the same way. There's a left edge and a right edge, and again, that will be different for some types of particle simulations. And this particular data set is not cosmological. Now, if you're not in astronomy, all of the data sets will be non-cosmological. So in this particular case, that's what you'll see as well there. So the first thing I'm going to try out is I'm going to say ds.printstats. This is a very common operation for things that are astronomy data, for adaptive mesh refinement data sets. And I want to point out a couple things. Until this point, the data set was a very lightweight object. So what YT does when it first loads a data set is it doesn't do any more indexing of the data on disk than is necessary. So this should be a very lightweight operation, even for the very largest of data sets. It goes and it grabs whatever metadata it is able to. It parses that metadata and sets up things like units, figures out what time the simulation is at, and so on. And it generates whatever information it can without actually reading in any data. One of the reasons for that we'll see a little bit later, is that we want to make it easy to generate time series where you may not know which data set corresponds to the exact time that you're looking at. And so we want to make it fast to iterate through just looking at the metadata that is available. You'll see that for this particular AMR data set, it shows how many grids are at each level, the number of cells, and so on. And then it gives us a total value here. And it also tells us a little bit about the data set. So, this is the time. It's about 4.43 10 to the 8 years, and so on and so forth. It also, during this process, takes a look at what is accessible on the disk. And what that means is that it figures out which fields are stored in the data output files and are thus accessible to us as we are trying to read the data. We can see those fields here by looking at DS field list. YT has a particular convention for how it regards fields. Whenever you are to specify a field, you specify a field type and a field name. And this is useful for a couple of reasons, but the main one is that occasionally there will be multiple different types of field that include the same field name. So this shows up, for instance, if you have multiple different particles that all store particle position X, or if you have multiple different fluid fields that are overlapping that have the same set of values, or in unstructured mesh, if you have multiple different mesh objects that all store the same type of connectivity or that all store the same type of vertex values. They may not be compatible with each other because they have different connectivity information, or they may be different element sizes and so on. So here we see that there are all creation time, and that refers to all of the particles in the simulation store a creation time. All of the particles store a dynamical time. And this is a special case of particle types called a union, where it takes all the different fields that are accessible and then concatenates them. There's also the ENSO field type, which are all the fields that are accessible on disk that are output by the simulation code. And you'll note that these have names like cooling time, BX, HII density, HI density, that aren't necessarily meaningful outside of the ENSO system. And then there are these two different particle types as well that we'll cover a little bit later. From this, YT knows how to generate a number of different fields. So I'll give an example of that. Here on disk, ENSO stores density with a capital D, and its density. YT knows that that corresponds to the density of gas inside, or the density of gas. So what it does is it constructs a translation field where the field type is gas and the field name is density, but with a lowercase d. This comes in handy because it means then that any other any other data set type that stores its data as whatever, if it's corresponding to a gas density that is compatible, it is also translated into field type gas with a lowercase d density. So that means that if I were to access the gas density field in a script on an ENSO dataset, I could utilize that same script to access the gas density field inside a Flash dataset or an AMRX dataset or a Pluto dataset or even a Gadget dataset, anything that corresponds to that type of translation. So let's take a look at what our derived fields look like. I mentioned that YT generates a number of derived fields. They are going to be a superset of the fields that we saw originally. So if we look at ds.DerivedFieldList, you'll note that there are a number of different field types. And you'll see that here all the ENSO fields are also listed in that. But we also see a number of gas fields down here. So YT constructs a set of translations. So it takes ENSO's electron density, and this is, it's a bit of a funny thing in ENSO, particularly with electrons. But let's say it takes ENSO's helium-1 density, and it translates that into a tokenizable and uniquely determinative field name. So helium-1 becomes helium underscore P0 for +0 density. So we have P0 fields for +0 for the non-ionized state, P1 for singly ionized, P2 for doubly ionized. And we also have things like fraction, mass, number density. Those are easy enough to generate and to understand, but we also generate things like the momentum, the magnitude of the angular momentum. We'll talk about that in a few minutes, where I go through how field parameters are set, but this can take in a center as a parameter to a field and then generate the magnitude of the angular momentum about that center. YT can also calculate things like the dynamical time, the emission measure, for velocity, the Mazoto weighting, and so on and so forth. It's important to note at this point that all of these different fields are not generated until we request them. YT knows how to generate them, but it does not generate them until we ask for them. The very first thing that folks ask after we look at this list of derived fields is, how do I know exactly what it's doing? So YT has built-in functionality in order to find how fields are generated, and it used to be that we would do things like ds.fieldinfo vorticityx.getSource, and maybe we would print that out. And you'll see that it generates this, and this is Python source code. But we also have a field browser. So if I just type ds fields, and if I'm in a Jupyter Lab environment, YT will output this widget. This widget includes tabs for each of the field types. And then here, it has the source code for those fields. So for instance, for the all particle type, I look here at age, and it shows me the source of that field. In some cases, there will be variables specified in it. So for instance, particle angular momentum. If you look here, def particle angular momentum, you'll see that it has variables like p-type. And here you can see that specifically p-type is generated. It's of type string, and it has the value all. So in this particular case, because this is all done with Python closures, the p-type is listed right there as a variable that we can inspect. And if we look at things like the electron fraction, we can see here return data f-type, where the species and f-type over density. The species here is L. So we can see that it's resolving it as as species L density divided by the density. In some cases, and in particular for all of the fields that exist on disk, you'll see that there's this null func. That just means that if it's trying to generate that, then something has gone wrong. I'll be working on improving that sometime in the future, but this just means that it's on disk if it's a null func. We can look at things like angular momentum x. Here is specific angular momentum x, so let's go down here to specific angular momentum x. You'll see here it's actually calling a bunch of different functions. So obtain the relative velocity vector on our data object and so on and so forth. So you can see how each one of these fields are generated. There's some other metadata that is stored about these objects. So we saw earlier that, and I will probably clear this output before I upload the notebook, but we saw earlier that there were things like the domain left edge and the domain right edge. So if I were to put in here domain width, we have a little widget that allows you to convert between different units. You see, this is what it is in code length, but I can also convert it to feet if I wanted, centimeters, megaparsecs. You'll see it's it's just over 1 megaparsec. I believe that that's an artifact of how the simulation was run. Any three-length array that's unitful will return an object like this, where we can convert between the different values in line. These arrays are also accessible programmatically. So if I were to look at domain width, I could say something like in units kpc, and it returns to me a unitful array in those units. And if I were to say get if I wanted to divide this by a 10 times yt.units.feet, it would give it back to me like this. So these these arrays are all unitful. They utilize a system that was designed for YT called UNIT, UNYT. And the reason that we have this system here is that each one of these objects is associated with a full SymPy registry. In particular, for systems that are based in cosmology, this is really important because we want to be able to have multiple different systems simultaneously that are manipulable, that also have different values for code length. So in many of the simulation codes and data sets that we utilize, the code length is scaled to some characteristic of the simulation domain. That might be different based on each individual simulation data set even. So each one of these is associated with a full SymPy symbolic math system. You'll see here this is a unit quantity and this is a SymPy symbol, and we're able to manipulate them. So you can take things and simplify them along different dimensionality axes. And we'll see that in a little while. YT also has a number of different aspects of the index structure, things like the grid left edge and so on, but that's not terribly important for what we're going to talk about today. But the important thing to note is that it simultaneously makes accessible high-level operations in order to manipulate the data and construct visualizations and analyzed processed subsets of the data, as well as access to the raw underlying data inside the simulation or the data set object. So here I'm accessing an individual grid, and I'm able to modify it and look at it and so on. And similar things are accessible inside Gadget, Flash, other data sets as well. The final thing that I want to show before we start moving on to how we can select information about data sets and take a look at things is, excuse me, I don't know about you, but I had to get up early to watch The Mandalorian before anybody else woke up in the house. So we want to be able to access information about the data set, and in particular the metadata. So if we look at ds.parameters, this is a full data set of all of the metadata that YT was able to collect. Now, Enzo is very verbose in the metadata that it outputs, and so what you'll see is that every parameter here, many of them will be default. This one looks like an int overflow, but many of them will be default, and they will cover a wide variety of things, and that's just sort of a thing that Enzo does. We'll see how that looks for other data sets in a few moments. I'm going to deviate from the Quick Start notebooks for just a moment to show you one of the things that we installed earlier. We installed something called Widgets. Widgets has built in a dataset viewer. It has a couple of different things in it. We will see them in a little while. But the thing that I want to show you right now is what's called a dataset viewer. If we say widgets.datasetViewer, and I'm going to assign this to the variable DSV. And then we say dsv.widget, and we call it like a function. Oops. It comes up with a set of visualizations of the data set that we are currently looking at. So the first one is a three-dimensional scene. This utilizes Three.js of the positions of all the grids in the data set. And you'll note that these grids are colored according to their level, and we can do cool stuff like change the color map and whatnot. And we can turn on different grid levels and so on, but that's not nearly as useful as just being able to get an overview of the data set. And really this is there are a lot of possibilities for what can be done in this, and we're only starting to explore that. So right now, it's mostly useful for getting an overview. But it also includes our field viewer, and it also includes a parameters viewer. The parameters viewer is one of the more useful items in here, particularly if we're dealing with data sets with large amounts of metadata. It has the domain left edge, the domain right edge, and the domain width, all listed here. And then it also has a nested representation of our metadata. So for instance, if I'm interested in refinement properties, I can say refine, and you'll see that it well, it doesn't look like it actually does much, but there we go. I can type a filter and it'll highlight the items that are in there. But it allows me to browse all the different items that are accessible inside our metadata, and in many ways in many cases that's pretty useful for understanding the data set or browsing it. And all of these things are accessible through our scripting interface as well. So let's move on and let's talk about how data is accessed inside YT. So I had mentioned earlier that until you actually request a field in YT, that field's data is not generated. At this point, we haven't requested any field's data. So no data has been loaded from disk. Yes, HDF5 datasets have been opened and looked at, and a little bit of inspection has been done, but nothing has been actually read into memory. So why don't we take a look at how we can do that? There are a number of different data objects that we can access inside of YT, and they all hang off the DS object, or our dataset object. So, for example, there is a ds.sphere object. When we call ds.sphere, we specify our center and then our radius, and it returns to us a sphere object. So typically we assign that to a variable like sp equals, and we can look at sp and we see it there. You'll see that it's a YT sphere. Galaxy 30 is the data set at this center with this radius. Let me break down exactly what we're saying here. By default, units supplied to YT in data selection are in code units. So by default, this is a code radius of 0.1 sphere. And we have specified that the center is at C. C here is the domain center. Both of these parameters can accept different pieces of information to make them easier to access and more useful. The first example of what we can do is, instead of C, we can specify a location. And you'll see now our center is no longer at the center of the domain, but is now at 0.4 in code units, 0.4 and 0.3, with a radius of 0.1. The second thing that we can do is we can specify any scalar unitful value can be specified as a tuple of a specific type, or of a specific form. The first entry is a scalar value, and the second entry is a string corresponding to the units. So in this case, I have said 10 kiloparsecs. You'll see that I specified that inside parenthesis. And you'll see now radius equals that cm. Why don't we change that? Let's make it 1e21 centimeters. You see now our radius is 1e21 centimeters. YT takes this and turns it into a unitful scalar. This sphere is now a ready to access data. We can either access our data manually by doing something like sp and then accessing it like a dictionary. And we can ask for things like gas density. Oh, it's a very small sphere, so why don't I go back up to 10 kiloparsecs. And we will center it at max. Or yeah, we'll change this we're now, instead of centering it at C, we're going to say max of density. Oops. Has to be max of gas density. We'll just say max. And we can now access sphere gas density. And it returns to us an array. That array is reasonably large, 425,000 entries. And we can modify that array the way we would normally modify any NumPy array. And that works fine for if our array can exist in memory. We can do things like max, min, and so on and so forth. But YT provides facilities to do this in a memory conservative way. As soon as I say SP gas density, it loads the entire array in memory, and it stays in memory. However, we provide a number of array-like interfaces to our data objects. We'll talk about other data objects in a few minutes, but for now, we will look at the sphere and see what we can do with it. Rather than calling max on our array, we can call it on our sphere object. In this particular case, because the data set is not terribly large, it is not of high advantage to do this. However, in the case that the data set is large, what YT does is it distributes, or it chunks the data off of disk so that it only loads what it can handle at each time, and then performs partial reductions on each of those sub-chunks, finalizing with a full reduction at the end across the partial reductions. There are a number of different operations that are implemented in this way. Stuff like min, sum, and so on and so forth. Let's try that. Sum of gas mass. And that gives us the total amount of mass inside our sphere, which in this particular case is 1.65 times 10 to the 9 solar masses. Could probably do that in slugs. Is that it? Yeah. There are some other things that we can do with this that I will show in just a moment, but first let me talk about other types of regions that are implemented in YT. YT implements spheres, which we've already seen, but it also implements axis-aligned rectangular prisms, which we will go into depth on in just a moment, and it implements Boolean objects. Boolean objects we'll come back to in a few minutes because first we need to get to some of our visualizations. It also implements items like lines or rays between different points, and you can do point queries as well. The next thing we're going to do is we're going to take our sphere and we're going to integrate our gas density, and we are going to integrate that along an axis. And then we're going to plot it. So one of the things that is neat about the way that we are setting up our data objects here is that because we're operating on them at the level of the data object instead of at the level of the array, they retain all of their spatial information. So we can integrate along an axis. So let's integrate along gas density, along the z-axis, and then output a plot from that. You'll see here is our plot, and right there is our sphere. Everything else is set to 0, and our sphere has values within it. Let's assign this to a P for a plot, and let's zoom in by a factor of 10. So this is the very first thing, first visualization that we've made. And what we've done is we've created a sphere, and then we've integrated all of the values inside that sphere, and then produced a plot from it. So you can see here the cell outlines where the sphere is, at the edge of the sphere, where the cells only partially intersect with the sphere selection. And you can see the center of this isolated galaxy here. Now I've assigned it to a variable and then I've called zoom on it. This time let's only zoom by a factor of 5. You can see now we have YT has modified the axis display so that it's in somewhat more useful units. But we have a fully featured plot that includes unit full information. And in particular, I want to point out that we generated this plot by integrating. Integrating here goes across variable length cells. Oh, yes, I will talk about that in just a moment. So the question in the chat was, can you talk about more about how the spatial information is kept? Was it because YT keeps it as a data object? Yes, I'll talk about that in just a moment. I want to mention that because we integrated, you'll see that here the density, which is stored as grams per centimeters cubed, because the path length is multiplied by the values at every step in the integration, the centimeters drops down to grams per centimeter squared, and so this becomes the surface density, or grams per centimeter squared. Yeah, so the reason that the information is kept is if we were to say SP gas density, this array is now almost completely disconnected from all the other columns in our information. So if we were to look at something like index x, we can get all of our x values and so on, which then can be used for generating spatial information. But because we're calling it directly on the data object itself, the reduction happens before the disconnection from the data object happens. So if we do SP, gas density, this array no longer knows anything about where this value corresponds to in the sphere. We can assume an ordering, but we can't assume that ordering is consistent as soon as the array passes out of the hands of the object. So if we call our operations on our spheres themselves, we can see YT is able to introspect and see where those values are. So if we look at something like sp.max, here we can say gas density. You'll see it gives us that, but we can also say axis equals x. And you'll see here it does a maximum intensity projection. So here it's grams per centimeters cubed instead. We can zoom way in, and we can see this is along the x direction instead of the y direction, or the z direction. So the reason that it keeps the spatial information is because it stays connected to the data object, rather than operating on the array that has been generated from that data object. So in fact, we couldn't take this and turn it into a maximum intensity projection without also knowing all of the corresponding x, y, and z values. I guess we wouldn't necessarily need the z. Well, we're doing it along the x, so it's actually y and z, but okay. Okay. So I'm going to go for a few more minutes, and then I'm going to take a short break. But in just a few minutes, I'll take that break. And it'll only be for about 2 minutes, so that I can scarf down a store brand Nutri-Grain bar. So we have other objects that are accessible inside YT. Things like the region, which accepts a center, a left edge, and a right edge. We've got disks, for instance. They take a center, a normal vector, a radius, and a height. So they can be axis misaligned, for instance. We can do ellipsoids, and each one of these has examples of how to generate one. But the handiest way of accessing information from a data set, in my experience, tends to be the .r object. The .r object is a region expression object. The region expression accepts a slice. So we got this idea from something in NumPy called mgrid. What mgrid does is it takes a start, like 0.1, a stop, like 0.2, and either a number of steps, in this case that's 128, because I'm multiplying it by j, so it's complex, or a size. So if I say 0.05, that is the step size, and it is non-inclusive. If I say 128j, it returns to me an array that is 128 long. This also accepts multidimensional access. So then you get an x out and a y and so on. And we've used that same concept here with the dataset object in a region expression. So we can say our region runs from 0.1 to 0.9 in the x, 0.45 to 0.55 in the y, and 0.3 to 0.9 in the z. And this returns to us a YT region object. It has a center that's calculated from these values. It has a left edge and a right edge. And this is now a box. We can say what is our left edge, and we can see that it in fact is the values that we've plugged in. And we can do the same operations that we did before. Now with a region object, YT knows how to grab the bounds a little bit better, and so you can see that it's restricting ourselves to the correct aspect ratio here. This is a little crowded, but that's probably something that can be worked on. There's more that we can do with this, though. In fact, we can utilize slice notation more broadly here. So I can say, give me a region that takes everything in the x, everything in the y, and is at the coordinate 0.5 in the z. And YT interprets that as a slice along axis 2 at this coordinate. And so if I wanted, I could take a plot of that. And this is now a slice plot at that coordinate. Okay, I'm going to take just a moment to scarf my store brand Nutri-Grain bar, and then I'll be back. So, probably about 2 minutes. Um, all right. Okay, welcome back. So let's move on to a little bit more of a deliberate introduction to uh, visualization. But before we go, before I dive back in, I wanted to make sure if everything is okay with the sound and everything. Let me know if it's not. And additionally, if folks have any questions, please go ahead and ask them whenever. Okay. All right. Let me go ahead and go back to our coding screen. So now I've promised a couple times that we would be doing data sets other than isolated galaxy. So I'm going to go ahead and I'm going to load up a different data set. And we're going to talk about particle data. So let me see. I'm going to load up Gadget Disk Galaxy. And we're going to talk about the ways that particle data sets are different than grid data sets, and the different things that we can do to make them look the same in some ways. So I executed the command yt load underscore sample, and I supplied the string gadget disk galaxy. I will note that I'm using load underscore sample today because today is day one, as it were. Starting tomorrow, we'll be using probably .load a lot more, so that we can get an idea of how to load things that exist on disk and so forth. So here we have a data set, and you'll note that it loads up a number of things that are similar to what we saw before. It calculates the time based on what it knows about the gadget time routines. It computes a domain left edge and a domain right edge based on the parameter file. And you'll note that here it says parameters domain dimensions 111. What's different about the way that YT handles particle data from how it handles grid data is that it doesn't try to grid the particle data. In fact, until the very last step, until the actual visualization, particles are never turned into anything other than particle data unless specifically asked to do so. So in previous versions of YT, like YT3 for instance, we would construct an octree and then like smooth on the octree and things like that in order to create stuff. And then for YT 4.0, we underwent a process called the demeshioning. In the process of the demeshioning, what we did was we removed everything that tried to turn particles into grids. We can look at ds.parameters, and we can see a number of parameters that are relevant and drawn directly from our data set. And you'll note that there are a couple things here that are kind of neat. So we have a numpart total, and this tells us the number of particles of each different type. If we look at our ds object, and this is true across across grid data sets as well as non-grid data sets like this one, there is an attribute called particle types. If we look at particle types here, let's do particle ds.index first. So if we do ds.index, it allocates an index and it reads over some of the data that exists on disk, and it constructs a hierarchical index of where particles exist on disk, so that when doing object subselection, it can read the smallest amount of data possible in order to get the data that is being requested. There are a number of different things we can specify to tune this. You'll see that it has index order 1 and index order 2 and so on, and we're not really going to touch that. And now if we look at particles by type, particle types, you'll see that we have particle type 0, 1, 2, 4, and 5. And if we look at our numpart numpart total, you'll see that each one of these corresponds to one of those. We also have the all type and the n-body type. If we look at ds.particle type counts, this is a dictionary that tells us how many particles of each different type are in our data set. Using some of the stuff that we talked about before, we can do a sphere with 10% of the domain width as our axis. Oh, that's actually not what it's going to do. We'll see that in just a moment, but here you'll see that the sphere radius is 0.1 of code length, but if we look at our domain width, oops, code length goes all the way out to 64,000. So how do we get around that? This is 0.1 in code length. We can specify 0.1 in what's called unitary. Unitary is a special unit that gets initialized for each data set that is scaled to the size of the domain. So if I say 0.1 unitary, that's 10% of the full domain. And there, if I look at this in code length, you'll see that it's 6,400, which is 10% of our unit radius. We have access to many of the same operations. I can do sp.max of gas density, and it computes the maximum gas density for our particles. And this is the density of the individual particles. And we can also do integrations. Oh. Here. So I can say integrate gas density along the x-axis and plot our density. And YT will go out and it will actually integrate all of our SPH particles and plot them on our data set. Let's call this plot P. And let's zoom in by a factor of 10. Let's zoom in by another factor of 2. You can see all these itty-bitty bits of gas. So I'm going to take just a moment to talk about how we are managing this plot and what this plot does. With grid-based datasets, computing the full projection at the highest possible resolution, because it's a piecewise continuous field, is straightforward. So YT pre-computes a quad tree that then when you do things like zooming, panning, changing a number of different characteristics, it doesn't need to retouch the data that exists on disk. It has everything that it needs to generate new plots already in memory. With SPH data, on the other hand, while there are techniques that you can use to do that, what YT does in order to preserve the fidelity of the data set is it recomputes the SPH kernel for all of the pixels that are inside the viewing window. That gives us a much higher fidelity visualization so that we can see what's going on inside our simulation. And it also allows us to be much more careful about the smoothing kernel as well as the output resolution. So for instance, now we have this plot, and were I to zoom in by a factor of 5 again, YT identifies the data that exists within that sub-region, reads it, and then recomputes the smoothing kernel for those values. You'll note that it does take a moment, and part of that is a result of the fact that we don't do any caching of data, which is something that we're looking at improving in the future. But as we zoom in, you can see that there are no gridded effects here because it is computing the smoothing kernel at each one of these locations. So I've been doing a couple different commands here, and I'm going to go ahead and talk through what it is that we're seeing. So here, I said P is equal to integrate on our sphere the gas density along the x-axis, and I plotted the density. What came back to us was a matplotlib plot that has a number of modifications to it that make it easier to use for the systems and situations that YT can be used in. So for starters, It has a field name over here on the right-hand side that reflects what the data set is internally, with units that it computes based on how the data set has been integrated, and we'll talk about that in just a moment because we can change those. It generates with a default color map. This one is called Arbra, and then it has access to the units on each side. As we zoom in, you'll note that here it actually gets a little bit funny because of how the origin is set up. But let's go ahead and do something slightly different. We'll say ds.r, and we'll just get everything. And we'll say integrate gas density along the z-axis, and then we will plot gas density. So remember that our region expression can accept left edges and right edges, and if we just say everything, it looks like this. So what are we seeing here? It's common in many of these simulations to only have gas particles in one specific region, and that's what we're seeing here. If we were to plot the particles that are n-body as opposed to SPH, we would see particles everywhere. But we now have a plot, and we can do a number of different things to it. You'll note that here it starts at 0 megaparsecs, goes up to like 32 megaparsecs. We can change our origin. Oops. We'll set our origin to be the window. That puts it there. And now if we zoom in, you'll see that we always have our origin set to be whatever is in the window. So here we've got 0 megaparsecs here as our origin for our window. This is independent of the domain, and if we were to set our origin to be something different, such as domain, we get it back, and our origin now runs, or our origin starts at wherever the left edge is with respect to the domain left edge. The Matplotlib objects are accessible inside this, but for now we're going to stick to just what YT provides. YT provides zoom operations, it provides pan operations, both absolute and relative, and it also allows you to set the units on any of your axes. So we can set our axes unit here. Let's say that I want this to be in KPC. You'll see now Y KPC starts at 1.3, goes to 1.8. And if I zoom in by a factor of 10, you can see all of our little gas particles here. And I think that we probably want our origin here to be in a window form. And so now we've got 0 kiloparsecs there, and kiloparsecs there. But I'm particularly interested in what's going on right around here. So let me go ahead and pan relative. Pan relative takes two values, the x panning and the y panning. I'd like to pan by 0 in the x, and this is all as a percentage or as a fraction of the height. I'm going to pan by 0, and I'm going to pan down by a factor of about 0.45. Oops. It takes a tuple. So now we're centered on this other this galaxy here. But perhaps I want to set my unit. So I call p.setUnit, and I have to specify the field that I want it to set. And I'll mention why that is in a moment. But it's because you can have multiple fields plotted simultaneously. And let's say that I, instead of wanting this in grams per centimeter cubed, let's say that I wanted in msun per mpc cubed. See, now it gives me msun per mpc cubed. And I can get an idea of the surface density of our image. I know it's tacky to comment, but down to 4 viewers, so thank you so much for hanging out with me here. We can also do other stuff. I mean, things that you're probably pretty comfortable with. I can set the gas density color bar to be something different. Oh, we didn't run a release of that. I forget, did we still have Hypnotoad? No, probably not. Let's do dusk. So you can see we can set it to a couple different items. I think Cameron came up with this color map, if I remember correctly. One of the other neat things that we can do is we can annotate on this. So we've got a whole bunch of different annotations that are possible, and I kind of love these. I'm going to go ahead and annotate a sphere. You'll see this takes a center and a radius. Let's say that our center is C, and our radius is 0.1 unitary. Now, okay. Let's do p.reset callbacks. Oh no, it's clear. So we're going to clear our annotations, and here I'm just going to do ds.domain center. It's not visible there, so let's zoom. Let's set our width to be 1.0 unitary. That's fun. All right. Well, let's go ahead and clear our callbacks again, or clear our annotations. I'll show you a different one. We've got a whole bunch of things that we can do here. Let's go ahead and annotate stuff like, let's see. We can annotate an arrow. The way that we take an arrow is you've got a position, overplot an arrow pointing at that position for highlighting specific features. So let's go ahead and annotate an arrow pointing at something in code units. 1,000, 1,000, 1,000. You see, there it is. It's pointing right at 1,000, 1,000, 1,000. So that's in data units. And so now, when we zoom in, it's not going to be there because it's off screen for our data units. No more arrow. But if I were to annotate an arrow pointing at, say, the center, we've got our little arrow there, and I pan. It knows where it's to point in data units, and so it continues to point there. You see, there it is. It's a little bit smaller. Okay. All right. Once we've got our plot the way we like it, we can save it to disk. If we just call p.save, it generates a nice little file name for us, and it saves it right out to disk. You'll note that it includes information about the data set, the axis, what the plot is, and the field. Okay. So let's do something a little bit different. I'm going to create a data object, and in this case, that data object is for the entire region. There are a number of different things we can do here. We can compute the mean of the gas density, and it gives it to us there. We can also compute the mean of the gas density, weight it by the mass. You see that it's slightly different. This is the arithmetic mean. This is the mean with the weight. And we can even do stuff like weighting it along an axis. Now, in this particular case, it's not super useful. Well, it depends on the discretization, but we can plot our gas mass mean here and so on and so forth. Now, let me see if I remember correctly. Going out on a limb here. Nope. Nope. Okay. We can also do stuff like, so we've seen a fair bit of generating visualizations, doing things like computing along axes. We can also do profiles. So profiles can be one or two dimensional aggregations, where it's no longer along a spatial dimension, but instead along a non-spatial dimension. So we have our data source, DD, and we can conduct a profile. We can specify multiple fields that we want to bin according to, and then we can specify how we aggregate those fields. So for instance, I want to profile these along the density field. And you'll see that I'm specifying a list of field tuples, in this case gas density, as the axis along which I will be binning. The next item that I specify is the field that I will be aggregating. So in this case, let's aggregate the mass, and let's specify that our weight field is none. And what we see from this is we get a one-dimensional distribution function of the total mass in each of our density bins. So each one of these bins is an accumulation of the total mass in grams. Now there are a number of different things that we can specify to this, but we can also get the x values from it, along with our mass. And so what we can do with this is we can set up our own plots. You have these plots from YT, but because we make all of the data accessible, you can also take it and plot it in your favorite plotting engine, even if that engine is Matplotlib. This works in multiple dimensions as well. So let's profile, and this time we'll profile along multiple dimensions. We'll do our first dimension being gas density, our second dimension being gas temperature, and we'll bin it gas mass with a weight field of none. And here we see the mass distribution in two dimensions. The temperature along the y-axis and the density along the x, with the accumulated mass in each of these two-dimensional bins reflected in the color. Now remember, this is a gadget data set, so each one of these is an accumulated particle. Because we're not generating a visualization from them that is spatial in nature, YT doesn't do any gridding of the data before computing this. The other thing to note is that this operation, dd.profile, is both memory conservative and parallel. So if you're running this in an MPI environment, which I don't think we'll be talking about during this workshop, but if you're running this in an MPI environment, it will distribute work to each of the individual tasks inside your MPI runtime. And then at the end, there will be an aggregation that produces the plot. Now, much like before, there are a bunch of different arguments we can specify to this. So I think we can say like gas density maps onto, or gas mass, we want to map onto msun. I think we can do that. Let's find out. Yeah, so you can have it do these things right at instantiation time, or you can also call set units on the resultant object and so on and so forth. This also makes our data available. So here, actually. So now prof2d we can call plot on, but we can also access prof2d gas density. Oh, sorry, prof2d gas mass, and we get a two-dimensional array that's 0 wherever nothing has been added. And for all of these, I've been specifying it with an average, with a weight field of none. Instead of doing weight field of none, let's weight them by gas mass. And instead of binning our gas mass, let's bin our velocity magnitude. So what this will do is it will accumulate along the density and temperature axes and it will average velocity magnitude with a weighted average based on the mass. So now when we call prof2d.plot, this is the mass-weighted average velocity magnitude in each one of these bins. See, we've got some hot, medium density gas up here that's high velocity. What we can interpret this as is we can interpret this as we can use this as a method of computing distributed averages, probability density functions, as well as characteristics of the gas itself. So looking at this, we have our velocity magnitude, which itself is not a field that exists on disk. The velocity magnitude, if we look at ds.fields, and we look at gas, let's scroll on down, velocity magnitude, looks like a translation function. Okay, part type 0, particle velocity magnitude, so let's go back up to particle velocity magnitude in part type 0. You'll see that it's the relative velocity in x, y, and z squared, and then the square root of their sum. So what YT does when we ask it for this, it splits the data up into manageable chunks, which are called chunks. For each one of those chunks, it accumulates inside our binning system, computing on the fly the velocity magnitude by reading the x, y, z dimensions, the density, and the temperature. My throat's getting dry. And then it clears the memory once it's computed its binning, and it accumulates this across all of the subchunks of our data. And this is again a particle data set. The next thing that I would like to do is we're going to move on to a slightly different data set. We are going to move on to a cosmological data set called ENSO Cosmology Plus. Because there are a couple things we can do with a cosmology data set. So here you'll note that I've said yt.load sample ENSO Cosmology Plus. It defaults to loading the final data set, but there are a number of them in this directory, and we'll take a look at that in just a minute. And now let's take a look at what the data looks like. I'm going to integrate it along the x-axis. You'll see it's not that high of resolution data. I mean, I believe the original name was, in fact, ENSO Tiny Cosmology, and then this is a slightly different version of ENSO Tiny Cosmology. So let's take a look at what happens if we generate a couple spheres. So I want a sphere that's roughly centered here. We're not going to do any halo finding today. But I want a sphere that's roughly about there. So let's take a look along another well, you know what? We'll just pick some spheres at random. We'll say sphere 1 is ds.sphere, center 0.1 unitary. And we'll say sp2 is ds.sphere, max 0.1 unitary. And if we were to do sp1 integrate gas density and plot that, so we've got it right there. It's right out in the middle of nowhere. There's nothing really there. If we were to do the same thing with sp2, looks a little bit better. We can also now combine these data objects. This is useful for if you have some mechanism, like for instance halo finding. And we can say sp1 plus sp2. This returns to us a new data container. That data container in this case is a YT Boolean container with an OR operation where these two data objects are combined. I'm going to call that dobj. And now let's integrate gas density and plot that. So now you see we have a data object. Our data source for our integration is the combination of these two items. We can do this with minus as well. So let's do ds.r minus dobject. We'll call this data object 2. So this is the full data set minus our Boolean data container. Oops. So we can do dobject2 integrate. You see now we've extracted out these two variable resolution environments inside of our data set. But let's take a step back and let's look at where some of the things that we can do with this. Now recall that if we wanted to, we can get an overview of the data set. With our widgets. And we can look at where the grids are. One of the reasons I didn't do this on the gadget data set was because even though we have some preliminary support for particles, it's not super reliable just yet, so we're not going to do that. We can see these are all the grids that are accessible, all our fields, all our parameters. Oh, and one thing I didn't mention is that there are these items here for looking along the axes. In principle, you can also add keyframes, but it's a little bit finicky at this point. See, it doesn't really do what it's supposed to. I guess splines are hard. Okay. So now let's get back to how we can compute physically meaningful quantities in the case that all of the fields that we are interested in are relevant or are accessible. So we have our sphere 1 and sphere 2, and recall that sphere 2 is centered on the most dense point in this simulation. There are a number of different quantities that are accessible. And you'll see there are things like angular momentum vector. If I compute the angular momentum vector by calling SP quantities angular momentum vector, I think I can also do, yeah, there we go. That's better. sp2.quantities.angular momentum vector. It returns to me the weighted average angular momentum vector for our entire object. We have a number of different slices, or number of different visualizations that can be used at this point, but the one that I want to see is I want to show you a slice plot. So we've seen how to generate slice plots before by using ds.r, but in this case we're going to use the slice plot object. We're going to specify our data set and our normal. Our data set is ds, our normal is L. We're going to plot gas density, and we're going to specify the center as sp2.center. This now constructs what's called a cutting plane. In this particular instance, the cutting plane is aligned such that the normal vector through the cutting plane is the angular momentum vector. This has all of the same panning and zooming that we saw before. It might not have pan actually, but it has zooming. I think it has pan. You see, as we zoom in, you can see where the cells, the finite volume cells, are cut through. And it doesn't do any smoothing on these, and so this is the actual set of values in our reasonably low resolution data set. We can also do a projection plot. We'll do ds with our normal equal to L. It also would accept x, y, or z. We'll center it there, and we'll specify our fields to again be gas density. So now, when we see, you'll note that it looks a lot smoother because it's using the underlying volume rendering framework, and it does interpolation along the path lengths. We'll go ahead and zoom in. So you see it does a bunch of interpolation here. So just to review, and then I'm going to open up for questions and answers, and if everybody hops off, then I will hop off as well. Just to review, today we talked about how to load in data sets. We loaded in both an ENSO data set and a Gadget data set with SPH fields in it. We talked about how to look at the different statistics of our data set, as well as the fields that are available. Oh, it's cool, Sean. The fields that are available, as well as the derived fields. We talked about how to browse the field information, how to look at our domain width and other statistics. I showed you a little bit of how to do data set overview using widgets. We also talked about what it means to integrate through a data set, as well as compute the mean along different spatial axes, how to select data quickly using the ds.r functionality. And then we talked about the differences between Gadget and ENSO datasets, as well as how to set things like the domain windows, the centers, pan, zoom, and how to make your plot look just like you want it to in data coordinates. We moved on to looking at profiling for 1- and 2-dimensional distributions of data sets. And then finally, we talked about how to do region selection using Boolean operators like OR. There's also an AND operator that I didn't show you, but an OR operator as well as a minus operator, which is a not operator. And then how to use those as input to things like our axes and so on. We finished up by talking about how to access different quantities on our data sets. So looking at quantities, and you have access to things like bulk velocity, the center of mass, extrema, max and min locations, sampling at max field and min field, and so on. And we'll actually go into those in some detail tomorrow. And then we finished up by looking at how you can both integrate along a non-axially aligned normal vector, as well as slice along a non-axially aligned normal vector. Oh, and we started out by installing YT. The final thing that I wanted to mention, I remembered as we were going through this, and then suddenly I've forgotten what it was. I guess that's pretty common. There's like a doorway thing where if you walk through a doorway, you forget everything you were thinking about beforehand. Oh, yes. I wanted to briefly mention that we'll talk more tomorrow. And tomorrow, if you're able to attend, we'll be doing what we've done here. We'll be starting with this as taken as given. And we'll be moving on to more advanced operations for data selection, particularly things like cutting above and below individual values. And we'll talk about what this means, but there are things like exclude above and exclude below that we will look at, and how we can use complicated data selection queries in order to do fully memory conservative distributions of values and quantity computation. So one example that I really like to think about is perhaps I just want to look at the hot gas and compute the bulk velocity of the hot gas in my data set. I will show you how to do that. Or if you want to just project or slice through data sets based on particular characteristics, we can do that as well. So that is, I think, where I will leave this. But I promised that I would be opening up for questions. If you would like to ask a question, please feel free to do so in the chat if you are able to. If you would rather ask inside the Slack channel, please feel free to do that as well. I have both open here. And I'm watching the viewer count, and if it drops down, I'll probably also hop off. As a reminder, all of this will be on YouTube as soon as Twitch lets me put it up there. And I will be posting the links at the end of the week, but they'll be on at least my personal page and probably also the YT page. And if they're not on the YT page directly, I'll make a playlist on the YT page that includes them. So thanks, everybody. And if you have any questions, ask away. I should mention I can't hear you, so I will repeat whatever questions folks ask. Oh, the time tomorrow is going to be at so tomorrow 8:30 to 10:30 Central Time. That's where I am. And if you are in, if UTC helps, that's 13:30 to 15:30. So 8:30 Central Time is 6:30 California, 9:30 East Coast, and then UTC, it'll be 1:30 p.m. To 3:30 p.m. Okay, folks. I think why don't we go ahead and call it there? Thanks, everybody. I hope this was useful for you, and I will get these notebooks up as soon as possible.